On Thursday, we defined radioactivity as a spontaneous, as a natural, as a random process whereby a nucleus will decay into something else. A lot of nuclei, in fact, the vast majority of naturally occurring isotopes of nuclei are not stable for whatever reason. There's a few reasons that we'll talk about in just a few minutes, but for whatever reason, the vast majority are not stable. So they'll break apart. They'll break apart into some smaller particle, some smaller chunk that breaks off, and then some other nucleus that's left over and kind of as a byproduct or as a result of that. For instance, we might take uranium-238. Uranium-238 has 92 protons. We know that it has 92 protons. How? Where are we going to find that information? Like, I don't memorize that stuff, right? You check your periodic table, you find that the atomic number for uranium is 92. Now, the mass number, the other number, the 238 that I was talking about, that changes depending upon the particular isotope. This particular isotope has 238 as our mass number, which means it has 238 minus 92 as our number of neutrons. What's that number? 238 minus 92? 146, I think. 146 neutrons. Now, that's unstable. That's unstable because there's too many protons. We'll talk about the details of that in just a moment again, but too many protons. And that makes the forces unstable, and the forces don't work quite right. They don't balance out quite right. So this nucleus saws off a little chunk. A little chunk of this nucleus gets sawed off and then goes off, flies off into nowhere land here. And that little chunk that breaks off happens to have 2 protons and 2 neutrons. We call that an alpha particle. Now, what are we left with? Well, it's not just like an alpha particle produced here and nothing. That would violate all kinds of conservation laws. We have to have an alpha particle get kicked off in an attempt to make it more stable, but we're left with another nucleus that just happens to be a little bit smaller. This time we're going to have 90 protons and 144 neutrons. We lost 2 protons and 2 neutrons as a result of this alpha particle that gets kicked out. Now, that's probably not stable either. That's probably still radioactive, but it's one step closer to being stable. This chunk breaks off in an attempt to make it more stable. The chunk flies off to wherever, and then this is what we're left with. We would call this uranium-238, the parent nucleus, and we would call this, what's 90? Thorium, I think? Thorium, what would it be? 234 would be what we would call the daughter nucleus. The parent is what we start with, the daughter is what we're left with. So we call this alpha decay, but it's not because an alpha particle decays into something, it's because rather something big decays into an alpha particle and then something else left over in an attempt to become more stable. We learned about 3 types of radioactive decay on Thursday. There was alpha decay, which comes from having a big nucleus, having a chunk that consists of 2 protons and 2 neutrons being sawed off and kicked off to the side, left with a slightly smaller nucleus. By the way, what's the other symbol for an alpha particle? 42He, because it's exactly the same thing as a helium nucleus. It is matter or energy. It is matter, and it happens because we have too many protons, relative to the number of neutrons, that is. Too many protons relative to the number of neutrons means we've got an imbalance of forces here. Remember we said there's 4 forces that act in the nucleus, 2 of which are relevant to this discussion. There's an attractive force known as the, if I remember that, strong nuclear force, good. There's a repulsive force known as the electric force. The electric can be attractive as well, right, but not in the nucleus. If the repulsive force, which is the electric force, is bigger than the attractive force, which is the strong nuclear force, then that means the nucleus will break apart. If the attractive force is bigger, then of course it's going to stay together, right? You got 2 people holding hands Okay, holding tight, that's the attractive force. Somebody comes and tries to push them apart, that's the repulsive force. If the attractive force is stronger, those two people are going to stay together. If the person that's pushing them apart is stronger, then the repulsive force will break that nucleus apart. Okay, let's talk about beta decay now. This happens for a completely different reason and releases a completely different chunk than the alpha particle. Beta negative decay, that can happen in just about any size nucleus. The chunk that breaks off of this is called a beta particle, which is identical to an, that's your hint right there. It's identical to an electron. Good. That's why sometimes we see the symbol for a beta particle 0 - 1 e. Is that matter or antimatter? That's matter, right? And this is produced by having too many neutrons, yeah. But that's not an energy, sorry, a force thing. That's an energy thing. The energy isn't right. The energy is unstable. The energy is bad. We'll say the energy is bad. Okay, and what happens as a result of that energy being bad? Remember the nucleus club? Well, kicks what out? Well, there's no electron in there. How do we kick an electron out when there's no electron in there? We get too many neutrons, so we change, not trade exactly, but we physically change a neutron into a proton. Because, look, you want to improve the neutron-proton balance, let's take a neutron and change it to a proton. But that in itself would violate the law of conservation of charge, because neutral became positive. That can't happen. So what else do we get produced here? An electron or a beta particle. And that's the thing that gets kicked out because I'm not part of the club. Beta positive, which is just another subcategory of beta decay. Beta positive looks like this. Sometimes we see it written 0 + 1 e. It's another name for a beta positive particle. It's not an electron, rather it's a positron. And is it matter or is it energy? Or is it? It's antimatter, and that happens as a result of having too many protons, yeah. But different thing that happens here than happens with alpha decay. The too many protons doesn't result in having a bad balance of forces. Rather, it makes the energy unstable, kind of like the beta negative decay. Again, the energy is bad. So what do? Well, too many protons. Let's take a proton and change it. Change it into a neutron. Well, that violates the law of conservation of charge. So, Zach, what do we got to have? We got to have an electron as well. No, sorry, almost. Not an electron, rather a positron. And that positron gets fired out because it doesn't belong in the nucleus club, right? Finally, we have gamma decay. Gamma looks like this. How many protons? 0. How many neutrons? 0. How many electrons? How many positrons? So what is this? This is energy, specifically electromagnetic energy, electromagnetic radiation. And this is kind of just a byproduct of something else that's already happened, right? The nucleus, as we said on Thursday, is left in an excited state. It doesn't want to be in an excited state, so it goes back down to its normal state by giving off energy. And that energy is released in the form of gamma ray photon. Now, let's rank these like we did on Thursday in terms of their ability to go through matter and their ability to ionize matter, to turn atoms into ions. What's an ion again? What's an ion, chemistry people? It's a charged particle, a charged atom. So it's the ionizing power is the ability to turn atoms into charged atoms, which, again, can result if it's in our bodies, anywhere else as well for that matter, but we care more about it when it's in our bodies, can result in strange chemical reactions that aren't supposed to take place, which result in strange biological processes that aren't supposed to take place, which can cause, we always hear of cancer, right? You know, of course, cancer is caused by by ionizing radiation, but so are other things like radiation poisoning and cataracts in the eyes and genetic mutations and so on. All right, let's rank them here. Which one of these has the highest ability to penetrate matter? Gamma rays. And the ability of gamma rays to penetrate matter is very high, very high. Like it'll go through several centimeters of lead or concrete. Which one's the lowest? Alpha particles. The alpha particles have a very low penetrating power. Like a sheet or two of paper will shield you from gamma rays. Your clothes will shield you from alpha particles. Beta particles, positive or negative, they're kind of the fence sitters in between, right? A couple centimeters of flesh. They won't go through your body, but they'll go beyond your skin. Now, their ability to ionize matter, it's flipped, right? It's like inversely related. The ability to ionize matter, we'd say alpha is very high. Gamma is, I don't want to say very low, but it's low compared to alpha, that is. So it's kind of a trade-off. What do you want to be exposed to? Well, none. But if you had to pick one, it depends upon the context, right? Okay. Alpha has a low penetrating power, but it's got such a high ionizing power. Honestly, something like alpha or beta, the bigger concern for you would not be necessarily being exposed to that radiation directly. The bigger concern for you would be either the byproduct of that, which could be gamma, which has a high penetrating power, or the consumption of something that was not had just generated alpha or beta, but the consumption of something that was radioactive that would produce alpha or beta. Right? So you drink water that's contaminated with radioactive material, and then it decays in your body. That make sense? That would be the bigger concern then. Beta, they're the fence sitters again. They can't decide whether they want to penetrate matter, whether they want to ionize matter. Listen, beta can't even decide whether they want to be positive or negative, for heaven's sake. So always remember that beta is going to be in the middle. They're the fence sitters, in the middle for everything. All right. Today, I want to go a little bit further with this. I want to describe the specific reactions that are taking place, what's produced, what we're left with, what goes into it. I want to describe that using what we call transmutation equations. Let's define transmutation first, though. Transmutation is the conversion of one element to another, which sounds an awful lot like the definition for radioactivity. But let me distinguish them. Radioactivity is a spontaneous, natural, random process where a nucleus decays. The actual change from one element to another is called transmutation. So in other words, radioactivity is an example of transmutation. Transmutation can occur by radioactivity, as it can occur by, we're going to learn tomorrow, nuclear fusion or nuclear fission, or some kind of artificial process. So transmutation is the actual act of changing one element to another, and that act can happen by fission, fusion, radioactivity, in one of a number of different ways. We can describe any transmutation, whether it's by fission, fusion, radioactivity, or any other way. We can describe them by an equation. An equation that's something like a chemical equation. In some ways, it's not like a chemical equation. We'll describe for you the difference in just a couple of minutes. Chemical equation, big thing is, there's lots of things you got to do with the chemical equation, right? Balance the numbers of atoms of this and whatever. But in the end, the most important thing is that if you got carbon on one side, you got to have carbon on the other side, right? Same number of carbon, in fact. But the most important thing is that carbon stays as carbon. And if you have lithium on one side, you got to have lithium on the other side. Hydrogen on one side, you got to have hydrogen on the other side. That's not the case here. We're not balancing elements here. Rather, we're balancing protons and neutrons here. So whether the element stays the same or changes doesn't really matter to us when we're analyzing the nucleus. That only matters in chemistry. Analyzing the nucleus, the only thing that matters is the number of protons and the number of neutrons stay the same. So to write a nuclear equation, we got to make sure that both the mass number and the atomic numbers both balance. They both stay the same on either side of the equation. As you take a look at your example booklet, example number 1. It says write the nuclear equation for the transmutation of radioactive isotope radium-226 undergoing alpha decay. What's our parent nucleus here? In other words, what are we starting with? If you want to use chemistry terms, you would say, what is our reactant? Radium. Yeah, radium-226. So we're going to write that on the left side. By the way, if it just said radium-226 without the 88, where would you get that 88 from? Sorry? Yeah, your periodic table, right. There's 2 numbers on your periodic table. We want the smaller of the 2 numbers. Now, that's all we start with. That's our parent nucleus. What are we left with? What's our daughter or what's our product, if you think in chemistry terms? We get an alpha particle. We could write that as 4,2 alpha, or we could write that as 4,2 He. It doesn't matter. The alpha particle appears on the right side because the alpha particle is released. This is what we got after the fact. Before, all we have is radium. But what else do we have? Well, we had 226 protons and neutrons. On the right side, we still have to have 226 protons and neutrons. We call that conservation of nucleons. A nucleon is a proton or neutron. We have to conserve the number of nucleons. Protons can change. Neutrons can change. The protons and neutrons combined have to stay the same. So 4 plus 222 equals 226. Now, we also have to have the atomic number balancing. 88 on the left side, 2 plus 86 on the right side gives me 88. How do you know what atomic number 86 is? Periodic table. I think you find that when you check that it's right on 222. Sorry? Let's take a look at the second one. This one says, write the nuclear equation for the transmutation of radioactive isotope lead-214 undergoing beta-negative decay. Our parent is lead-214. It undergoes beta-negative decay. So the beta particle appears on the right-hand side. Sometimes you might get an alpha or beta particle appearing on the left side, but that would not be alpha or beta decay. That would be some other process. Alpha beta decay, one of the products is the alpha particle or the beta particle. Products are daughter. What else? 214 goes to 214. 0 plus 214 gives me 214. I didn't ask anybody that number because I figured that everybody can add 0 and 214. No, I shouldn't, no. Minus 1 plus what is 82? This is one of the most common mistakes that are made in this entire unit, actually. Minus 1 plus what is 82? 83. What do you think people do? What mistake do people make with that? 81, yeah. A lot of people make that 81. 83 is bismuth. You can check that on your periodic table. Now I'm going to pull out another color here because there is something else produced here. It's called an anti-neutrino. It's like a V with a little line over it. The little line means the anti part of it. Wolfgang Pauli, you don't really need to know that name. 1930-ish, I think it was around 1930, hypothesized the existence of neutrinos and anti-neutrinos to account for some missing energy here. Now, at the time, it was purely a theoretical argument. Hey, we're missing something. This is what explains it, so it must be there. Now we know that they do exist. We've seen them in neutrino observatories. But at the time, again, it was purely theoretical. We don't have to add anything to it to make it balance. It just accounts for some energy in there. Yep. Let's take a look at example number 3. So let's write the nuclear equation for the transmutation of radioactive isotope Magnesium-23 undergoing beta plus decay. Beta plus. Might not be a bad idea to underline that, right? Beta plus, beta minus. Make sure you don't mess up on that. We start off with Magnesium-23. We end up with a beta particle. Remember, beta goes on the right-hand side. Oh, I made a mistake here, actually. What should that be? Beta positive. So 0 plus 1 beta. Balance out the mass number. 0 plus 23. Good. Equals 23. 1 plus 11. Josh? 1 plus 11 is equal to 12. What element is that? Sodium, yeah. Take a stab at this one now. What am I going to add to this? Yeah, that's going to be a neutrino. So neutrino is the matter and the antineutrino is the antimatter. Again, 1930, Wolfgang Pauli. Don't need to know the details of that, but just that they have to be there for beta negative decay and beta positive decay. Yep. Oh, sorry. Thank you, Nick. Thank you, Nick. That should not have a line over it because the line means the anti. Good. Thank you. So beta negative produces this antineutrino. Beta positive produces this neutrino. Alpha decay produces this nothing else. It's just the alpha particle in the daughter nucleus, nothing else. Example 4, part A. Complete the following nuclear reactions. So this time we have the daughter nucleus. We're just looking for the alpha or beta particle, determining what kind it is. Got to work in reverse a little bit. 30 goes to 30 plus what? 0. 15 goes to 16 plus minus 1. That's going to be a beta particle, right? Is that it? What else? Good. Antineutrino. Thorium-234, uranium-238. 234 plus what is 238? 4. 90 plus what is 92? 2. That's going to be alpha particle, helium nucleus, however you want to write it. Anything else there? Nope, that's it. Nitrogen-13 goes to carbon-13. 13 plus what is 13? 6 plus what is 7? Gotta be careful, because some people will put minus 1 there, right? That's going to be beta positive, or what's another name for that? Positron emission. Yeah. Anything else produced there? Neutrino. Good. Almost put the line over it again. And number 5, the last one that we want to work on here. It says complete the following artificial transmutation equations. This just means that we're not dealing with radioactivity in these questions. This is some kind of human-made nuclear reaction. In the first case, we bombard nitrogen with an alpha particle. This is not alpha decay. If it was alpha decay, alpha would appear on the right-hand side. Okay, this is some other process where we're trying to get the alpha particle to be absorbed by the nitrogen-14. 14 plus 4 is 18. 17 plus what is 18? 1. 7 plus 2 is 9. 8 plus what is 9? 1. What's that? Yeah, check your periodic table. It's not beta, it's not alpha, so check your periodic table. Tell me number 1 is hydrogen. Cadmium-105 plus a beta particle. This is a process called electron capture, actually. 105 plus 0 is 105. 48 plus minus 1 is 47. And atomic number 47 on your periodic table is silver, Ag. So even though it's not actually radioactivity, Doesn't change the way we do it, right? As far as analyzing the equations, transmutation is transmutation. Just balance the numbers. I'd like you to take a look right now, please, at worksheet number 24. I'll give you a little bit of time to work on that in class, and then we'll do a couple of them. And then we'll move on to talking about how quickly these reactions take place. Okay, let's take a look at 3 of these as requested: 4, 6, and 10. Number 4 says uranium-234 goes to an alpha particle plus what? Well, we'd say on the right-hand side, we need 234. So 4 plus 230 gives me 234. 2 plus 90 gives me 92. And atomic number 90 on my periodic table is, I believe it is thorium. Is that right? Okay. No neutrino, no antineutrino, none of that stuff. We're done that one now. 6. This is different. This is an artificial one. On the right side, we have 265 plus 1 is 266. So we're going to say 58 right here, meaning 208 plus 58 gives me 266. 108 on the right-hand side, 82 plus 26 gives me 108. And atomic number 26 on the periodic table is Fe, iron. And number 10, beryllium-9 plus hydrogen-1, another artificial transmutation equation. 9 plus 1 is 10. 6 plus 4 is 10. 4 plus 1 is 5. 3 plus 2 is 5. What's that? It's an alpha particle or a helium nucleus. But that's not alpha decay, right? That's not alpha decay because that's not a spontaneous decay of something into an alpha particle. That's artificial because we're bombarding beryllium with hydrogen to make this happen. Okay? Does that make sense? All right, let's do one more. I want to do just one more because here we are. Let's go number 8. That'll work. On the left-hand side, we have 214. Right-hand side, 214 plus 0 gives me 214. Left side, 83. 84 plus what gives me 83? Negative 1. Good. And that's going to be a beta particle, right? Good? What's wrong, Miguel? We got to have an antineutrino produced there as well.